everyone, welcome back to my YouTube channel. This is the third video in my data structure series. Today we are diving into one of the most fascinating topics in data structures, AVL trees. Ever wondered what happens if a binary search tree becomes unbalanced? Well, we make the self-balancing superheroes in the tree world. In this video, we will break it down step by step. What AVL trees are, why we need them, and how they balance using rotations. By the end, you will mastering AVL trees like a pro. So if you are ready to level up your coding skills, let's get started.
This is a unbalanced binary search tree. Now let's think about a normal binary search tree. Over time, if we keep inserting values in a sorted order, it can become extremely unbalanced. And what happens then? Searching, inserting and deleting elements becomes slow, almost like searching in a linked list. That's where AVL trees come in. Unlike regular BSTs, AVL trees are self-balancing. They make sure that the height difference between the left and right subtrees is never too large. This helps in keeping operations like search, insertion and deletion super efficient, always in or log n time. So how do AVL trees stay balanced? They use something called rotations. Don't worry, I will explain it step by step in a super simple way. By the end of this video, you will not only understand AVL trees but also know how to implement them in code. An AVL tree is a self-balancing binary search tree where the height difference between the left and right subtrees is at most 1. This means it always maintains balance, preventing it from becoming inefficient like a regular BST.
First, we look at into these numbers into a binary search tree. Now I explain how to build a binary search tree in these numbers. Firstly, this first element, we take it as a root node. Number 40 is root node. Then we compare this first element and second element. If second element greater than first element, we move it into right side. And if second element greater than first element, we move it into left side. I wrote it. Then number 40, number 60 less than greater than into number 40. Then 60 move on right side. Number 60 move on right side. Then we move. Then we compare number 3 and element 10 to second element. Then number 20 less than number 60. Next we compare third element into first element. Number 20 third element less than into first element. So number 20 we can move it left side because now you can why am I move it left side. Number 20 less than number 40. So we move now we can move it number 4 fourth element 30 also already less than 40. So we can move it into left side. And number 20 less than number 30. Therefore, we can move it into right side. Number 30. Okay, now we move on our fifth element 50. We compare into it our first element number 40 less than number 50. So then we move it into our right side. Next we compare this 60 greater than 50. So let's we move on to 60's left side. Next we move on to our sixth element. It compare first into first element less than, then it move into left side. Then we compare number 20 already also it less than into number 20. Then we move it into left side number 10. Then we move on our last element number 70. It compared first element number 40 70 is greater than. Next we compare number 60 70 already greater than. Then we move on into right side. This is the binary search tree, balanced the binary search tree. Now I will explain how to these numbers convert into binary search tree. This is done in the same as before. Firstly, the first element is a root node. 10 is a root node. Then compare second element into first element greater than this second element into first element. 20 is we can move into right side because 20 is greater than number 10. Then we move on now third element number 30. We can compare in the first element 30 is greater than number 10. Then we can move on right side. We move on this element. We want the compare number 30 into the second element. Number 20 is less than number 30. So we can move it into right side. You can see I have done it same as before. Why these two are different? The order given to change these two has been affected because this is not a balanced tree. Let's see how to balance an unbalanced one. To be balanced tree, it should be smaller by subtracting the subtrees on the left and the subtrees on the right side. The answers from this should be equal or less than number 1. Now you can see the formula. Now you can see an example. 40 is a root node, and you can see these three numbers. They are left subtree, and you can see this side, right side. This is right subtree. Left subtree height is 2. 1, 2. Right subtree height is number 1. We move on search balance factor. This 40 root node balance factor. Left side subtree has height is 2. Right side subtree height is 1. Then the balance factor number 40 is 1. 2 minus 1 equals 1. All leaf nodes balance factors are 0. Then number 20 balance factor left subtree. These are leaf nodes. Left subtree 0. Right subtree 0. 0 minus 0 0. Then already this is 0. These are balance factors of this tree. This tree is already AVL tree. If every balance factors is 0 or 1, it is an AVL tree. There are 4 conditions to convert a tree into a AVL tree. Now you can see the 4 conditions: right, left, right, and left, right. I will explain to you this with an example. I wrote an example. We will check is this AVL tree or not. Now you know how we can get a balance factor. This number 3 is a leaf node, so its balance factor is 0. Number 20 balance factor is 1, and 10 balance factor is 2. Then you can identify is this AVL tree or not. This is not AVL tree because the root node balance factor is greater than number 1. So how can we transfer this into AVL tree? We can use these 4 conditions for it: right, left, right, left. Do you know how can we use these conditions? After entering number 30, this graph was unbalanced. So we moved this 30 into right side, number 10 and number 20. So we can use the right condition for this graph convert into AVL tree. When there is right, we move it into the left side. I will show you. Left side, move on this left side. Then 10 move on the left side, 10, 20 left side. Then 20 is root node, 30 already left side, right side. This is the after converting right side condition. This is AVL tree. This is a binary search tree. So it also a AVL tree. Now we move to the another example. This is our next example. Now you know how to get balance factor. I already wrote that these balance factors. This is unbalanced graph. Now we want to this graph into AVL graph. So we can use these 4 conditions. What condition we use this? We can use this. We without 10 node, this balance factor 0, this balance factor 1. Then this is already a AVL tree, but this adding this after this already unbalanced. We move the 10 into left side. 20 into left side because 20 and 10 less than 30. So we can use left condition for this. We show how to apply it. We if we use left condition, then we can move these into right side. So number 30 into right side, number 20 is root not, then number 10 into left side. This is AVL tree. Now you can see another example. Since 20 was added here too, this will not be an AVL tree. I write the balance factors. This balance factor already 0, 1, 2. Now you can see this is not a balance factor. We want to this convert into balance factor. Now we want to search how to go on number 20. 10, 30 to right side and 30, 20 left side. So we can use this right left condition. If 20 is in left side, we move it to right side. And firstly, I will show you it. Number 10, number 20, and number 30. Then the number 10, we want to rotate left side. Now you can see number 20 is root not 10 left side, 30 to right side. This is AVL tree. Now you can see this is AVL. Now you can see our last example. Now you know how to convert this graph into AVL tree. We can use the right left condition. No, we can use this right left condition. Okay, you can see this right side element into left side element into right side. You can see number 30, number 20, number 10. Our next step is right side left side into right side. Then number 20 is root not left side, number 10 and number 30. This is AVL tree after converting left right condition. So that's the AVL trees. If you found this video helpful, don't forget thumbs up, subscribe and hit the bell icon so you never miss a future video on data structures. I have got more topics coming up, so stay tuned. I will see you in my next video. Keep coding.